Hello students, this is question number 4, JEE Advanced 2018. For every twice differentiable function, domain is all real number, codomain is -2 to 2. But we have one relation f of 0 whole square plus f dash 0 whole square equals 85. Then which of the following statement is true? So we have to check one by one all options. So option A. There exists a small r, small s belongs to capital R, I mean real number, where r is smaller than s, such that f is 1 an open interval r comma s. So it's a easy problem. Now we can check. We have to just verify whether function is constant or not in this case. So let us check. With this condition, f of 0 plus f dash 0, f of 0 whole square, f dash 0 whole square 85. But for all real numbers, fx cannot exceed 2. So f of 0 also lies between -2 to 2 because codomain is -2 to 2. Now if I do square, so f of 0 whole square is smaller than or equal to 4. It means if maximum of f of 0 is 4, it means it cannot, f dash 0 cannot be 0. So we understood, okay, f dash 0 cannot be 0. So f dash 0 cannot be 0, it means we at least we understood about to 0, this function is not constant. So if function is not constant, then function will be whether increasing or decreasing. If function is increasing or decreasing, then it is obviously one function. So option A is right. Now option B. So now option B. There exists x naught -4 to 0 such that f dash x naught modulus less than equal to 1. This is direct application of LMDT, Lagrange's theorem. So x naught belongs to -4 to 0. So f dash x naught we can write f of 0 minus f of -4 over 0 minus of -4. Now we have to think about this. For codomain, if we observe, we have -2 to 2. So it means fx can have values from -2 to 2. So f of 0 will have also -2 to 2 and f of -4 will have value also from -2 to 2. Now we need to find f of 0 minus f of -4. Okay? Now we need to understand right here. f of 0 maximum value of f of 0 can be 2. Minimum value of f of -4 can be -2. So 2 minus of -2. So maximum it will be 4. Okay? And minimum f of 0 can be -2. And minus of f of -4 can be 2. So -2 and -2. It is -4. So -4 to 4. We got f of 0 minus f of -4. Now, okay, we need to find mod f dash x naught mod. So apply mod here. So now we have to understand f of 0 minus f of -4 mod is obviously less than equal to 4. So this is less than equal to 4 and this is 0 plus 4. So this is less than equal to 1. So what we got? We got f dash x naught mod less than equal to 1. So option B is also right. Option A was also right. Now come to option C. What is that? So limit f of x tends to infinity equals 1. We have to check this whether this is right or wrong. Now we are considering fx is bounded, right? It lies between -2 to 2. but when x is approaching infinity, then the value is 1. So this type of question we are doing by some assumption. We will assume some function so that this condition will satisfy as well as this condition will satisfy. I mean, domain would be all real number and codomain will be -2 to 2. So I have to select one function, I have to write one function, and accordingly fx domain is all real number, but this is bounding. Okay, fx is bounded, which is -2 to 2. If we remember, we have bounded functions, then we can remember sin x, cos x. Sin x is also range from -1 to 1, cos x is also range from -1 to 1. So if I assume sin x, so I can write sin x, but I have -2 to 2 and domain is all real number, it's satisfied here. But this line is not satisfied because f of 0 is 0 and f dash 0 will be 2, but 2 square is 4 but not 85. So I have to again modify this function, so this is not valid. Okay, then I will write f of x is 2 sine of, this is 85 but it's square, so I will write root 85x over 2. Why 2? Because of differentiation. You can check here. Now take it derivative. F dash x is 2, sine derivative is cos root 85x over 2, and then just derivative is root 85 over 2. This 2 and this 2 got cancelled. We got f dash x is root 85 cos of root 85x over 2. So we got this. Now f of 0 whole square plus f dash 0 whole square we have to find. So f of 0, x is 0, then this is 0, and f dash is 0, this is 0, cos 0 is 1, root 85 whole square is 85. So we got 85. So it means our this condition is satisfied, this condition is satisfied. So I mean we have selected a valid function. Okay, but for this function, when x is approaching infinity, the limit is not coming 1. Why? Let us understand again. If I put limit in this, we have fx. Now limit x tends to infinity. So here I will write limit x tends to infinity. This is 2 and this is sine root 85x over 2. So this is 2 and this is when we put x as infinity, then it would be sine infinity, right? But sine infinity is an oscillating. It lies between -1 to 1. So we got total twice of -1 to 1. Okay? We got twice of -1 to 1, which is not constant, which is not fixed. So how can we say fx value when x is infinity is 1? So option C is wrong. Now it comes to option D. Let us understand. In alpha -4 to 4 such that f of alpha plus f double dash alpha equals 0 and f dash alpha does not equal to 0. We have to verify this statement is right or wrong. So what we have, f of 0 whole square, f dash 0 whole square 85. So if I consider a function, let gx equals f of x whole square plus f dash x whole square. Okay, where obviously here alpha lies between -4 to 4. So right now I am going to change everything between -4 to 4. So for example, if I want to draw graph of gx, then how it would be, let us understand. -4 to 4, okay, gx is f of x whole square plus f dash x whole square. So at x equal to 0, if I put, then it would be f of 0. Okay, what is g of 0? This is f of 0 whole square, f dash 0 whole square. But f of 0 whole square, f dash 0 whole square is 85. So at x equal to 0, this is fixed, this is 85. Okay, we understood. Between -4 to 0, f dash x naught is less than 1. We have to understand this. When x naught belongs to -4 to 0, we already proved this. F dash x naught mod is less than 1. So f dash x naught whole square is also less than equal to 1, right? So f dash x naught whole square is also less than equal to 1. Now again we have to understand, what is this? This is f dash x whole square, this is f of x whole square. Where fx whole square is less than equal to 4, because maximum fx reach to 2. If I add these two, then I can have, okay, and this right now since I am explaining between -4 to 0, so I am considering this one also x naught. So f of x naught whole square plus f dash x naught whole square less than equal to 5. So for example, if this is x naught, okay, so if this is x naught and let's say this is 5, it means when I am talking about x naught, okay, when I am talking about x naught, then sum of these two, f of x naught whole square plus f dash x naught whole square is less than equal to 5. So value of gx when x equals x naught can be 5 or less than 5. So, okay, I am considering this function or this value, okay. So it means, and since it is a twice differentiable function, so obviously it will be continuous. If it is continuous, then obviously from here to here it will cross like that, graph would be like that. So since we have already applied Lagrange's theorem in B part between -4 to 0, same thing we can apply from 0 to 4 also. And when you apply 0 to 4, then the thing which is happened to left side, same thing will happen to right side. Try to understand right here also. Okay, I am explaining between x naught dash belongs to 0 to 4 right now. Okay, apply Allen-Beatty theorem right here. So f dash x naught dash why? Because just I am taking different. This is x naught, it must be denoted by something else. That's the x naught dash. This dash doesn't mean derivative. This is a representation. So f dash x naught dash equals f of 4 minus f of 0 over 4 minus 0. Now apply both sides mod. So this is f dash x naught dash less than equal to 1. Why? Because f of 4 maximum can be 2 and f of 0 minimum can be -2. So 2 minus of -2 is 4 and this is 4, so 4 over 4 is again 1. So this is less than equal to 1. So now f dash x naught dash whole square less than equal to 1 and f of x naught dash whole square less than equal to 4. Now if we add, so f of x naught dash whole square plus f of x naught dash whole square, f dash x naught dash whole square less than equal to 5. So I told you in the beginning, I told you, so same thing will happen. So here also if I consider, like if this is 4 and if I am considering, okay, this is x naught dash, so at x naught value of this gx again, this would be 5 or less than 5. So 5 is here, so 5 or less than 5. So for example this one we have, and since it is continuous, so it will be like this. Okay, now what you are observing, you are observing this fx will reach 5 at 2 points, this one as well as this one. This gx will attain 5 value at 2 points, here as well as here. Okay, so I am considering this point as alpha 1 and this point as alpha 2. So till now what we have proved? We have proved g of alpha 1 must be equal to g of alpha 2 somewhere between minus 4 to 4, because here it is given minus 4 to 4. So here I can apply Rolle's theorem. So this is a really fantastic question of 2018, and I would say this is the most difficult problem, especially option D I am talking, not 4. Okay, so I have to erase. So now we have proved this is function gx. G of alpha 1 must be equal to g of alpha 2. Okay, then g dash alpha must be 0 by Rolle's theorem. So now we have to find g dash alpha. So let us differentiate this. This is g dash x, which is 2fx, and f dash x, plus this is 2f dash x, and this is f double dash x. So this is, for example, g dash alpha we need to find. Then this is 2. F dash alpha I can take common, because here it would be alpha and here it would be alpha. So here I got f of alpha plus f double dash alpha. Now put here. So twice of f of alpha bracket, sorry, this is f dash, this is f dash alpha. So this is f dash alpha, this is f of alpha, and this is f double dash alpha equal to 0. So now I got f dash alpha times f of alpha plus f double dash alpha equal to 0. Now either this 0 or this 0. We have to check whether f dash alpha can be 0 or not, when alpha lies between alpha 1 to alpha 2. Now we have to think this between alpha 1 to alpha 2, this is actually from at alpha 1 it is 5, at alpha 2 it is 5. Between alpha 1 and alpha 2, gx is always greater than 5. This is above 5, right? This is above 5. Now, when this is above 5, we have to think, this is above 5. So this is above 5 from here to here. So I will write greater than 5, okay? And we know maximum value of fx whole square is 4. So when it is 4, maximum is 4. So obviously this must be greater than 1. Because if maximum is 4, okay, suppose it is 4, then it must be f dash x greater than 1. So it means f dash x from alpha 1 to alpha 2 never be 0. And it lies here. So alpha 1 and alpha 2, it can lie between alpha 1 and alpha 2. So we understood if fx whole square maximum is 4, then this cannot be 0, it must be greater than 1. It means we understood f dash alpha cannot be 0. It means what? This must be 0. F of alpha plus f double dash alpha equal to 0. We got this result, and f of alpha of double dash alpha equal to 0 and f dash alpha does not equal to 0. Same thing. It means option D is also right. So it's really a good question, and this question is related to Rolle's theorem as well as Lagrange's theorem. So this is a bit tough problem and interesting one.